last two classes, we were struggling with the classification of elements. How to classify the elements. Earlier we had Dobereiner with his triads. Later we had Newland with his octaves. And finally we have learned the Mendeleev's periodic table. Okay. After a failure and success of the whole theory, okay, now we have a new scientist, a British chemist, whose name is Henry Moseley. In the year of 1913, he came with his modern periodic table. Okay, what was common in the earlier classification? In the three classification, the classification was based on the atomic mass. Okay, here we have considered atomic number as a criteria for the classification. When you talk about the modern periodic table, Henry Moseley suggested that atomic number is the standard accurate for the basis of the classification of elements. So what is atomic number? Atomic number is the number of electrons or number of protons of an atom is known as atomic number. So based on that, he suggested the modern periodic law. The modern periodic law states that properties of the elements are the periodic function of their atomic number. Okay, compared to the Mendeleev's periodic law, the periodic law has changed into the atomic number. Okay, so Mendeleev's periodic table has many drawbacks. He could not assign the position of isotopes, he could not assign the position of hydrogen, the irregularity in the mass grouping and all. Okay, when you look this classification, students, we know that when you take two consecutive elements, if you take boron and fluorine, okay, suppose a small example, boron and fluorine, boron with 5 atomic number, fluorine with 9 atomic number. So you can predict in between how many elements can come. Okay, you can easily say that after boron, carbon with 6 atomic number, after carbon it is nitrogen with 7 atomic number, after nitrogen, oxygen with 8 atomic number. So between boron and fluorine there are 3 elements. Without second thought, you can say that there are 3 elements are there in between. Anyone can easily predict how many elements can accommodate in between the two consecutive elements. Just now I have told you a simple example. Okay, so based on the modern periodic law, he has constructed a periodic table. Okay, so there he overcome the demerits of all the 3 classification which is put forward by Mendeleev. He tried to rectify the demerits of Mendeleev's classification. In his classification, he included isotopes also in a separate column. Okay, the separate column means if you have isotopes of hydrogen means the same column he included the 3 isotopes of hydrogen. If you want to accommodate the isotopes of carbon, he accommodated the same column of carbon. That was the merit of the periodic table, modern periodic table. So let us summarize. The first, he considered what? Yes, he considered the modern periodic law as a basis of the classification. What was the law? The law says that properties of the elements are the periodic function of their atomic mass. And finally, he rectified all the demerits of Mendeleev's periodic law, Mendeleev's periodic table. Right? Yes, he could assign a place to the isotopes. And atomic number was the standard accurate for the major classification of the elements. Because of the increasing order of atomic number, he has arranged elements in a periodic table. That was the beauty of the modern periodic table. Okay, let us go to the incredible journey of modern periodic table without losing time.
The modern periodic table consists of 7 horizontal rows
and 18 vertical columns. Just like Mendeleev's periodic table, here also the columns are called groups and the rows are called periods. Can you see a zigzag line over here? This separates metals from non-metals. And do you see these elements which lie on the boundary? These are called metalloids. For simple reasons, they have both the properties of metals and non-metals. Now do you see the bottom's two rows of elements here that are placed separately from the rest? These set of elements are called lanthanoids and actinoids respectively. All of these elements are metals and we will learn the property in the higher classes. Okay students, let us discuss the modern periodic table in detail. As we discussed, we have 18 vertical columns. The 18 vertical columns are known as groups and you can see the 7 horizontal rows. Okay, the 7 horizontal rows are known as periods. Okay, 18 groups and 7 periods. Okay, let us discuss the group and period in separate. Before that, I will give you a simple technique how to learn the modern periodic table at a look, or how can you draw this kind of a blueprint. This is a simple outlook, a simple blueprint of the periodic table. Just I have drawn to show you. Okay, so you can see the first group. First group means hydrogen to francium. Okay, hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. These are known as first group elements. They are known as alkali metals. First group elements are known as alkali metals. The second group, they are beryllium, magnesium, calcium, strontium, barium and radium. They are known as alkaline earth metals. Alkaline earth metals. Okay, and out of this you can see the group from 3 to 12. 3 to 12 means total 10 groups are there. The 10 groups are known as transition metals. Transition metals, or which is known as a small letter D, D block elements. Okay, and the group from 13 to 18, the group from 13 to 18 are known as P block. What we call P block elements. And this row is the lanthanide, and this row is the actinides, and this is the F block elements. Okay, this is the S block. A small letter S indicates the outermost shell electrons ends with the S subshell. That you will learn in the higher class. Here this 10 groups are known as D block because the outermost electrons are ended up with D electrons. I mean D shell. This is known as P block because the outermost electrons of these elements are ended up with the P subshell. Here the outermost electrons of these two rows are ended up with the F subshell. That is why we are called it as a subshell name. So you can separate it as different blocks. S block, P block, D block and last two rows F block. Okay. So children, when you look at the table you can see in the group wise, when you consider a group wise elements, the properties will be same. Elements with the same group having similar chemical behavior as well as one more factor. They have a similar valency. When you consider the first group, the old element possesses the valency 1. When you take the second group, all the elements possess the valency 2. All the alkali metals possess the valency 1. All the alkaline earth metal possess the valency 2. And the transition elements from 3 to 12, 10 groups showing different valency. The 13th group, that is boron. The first member is boron and this group is known as boron family. And this is the carbon Carbon is coming first. That is why it is known as carbon family. And this is nitrogen is coming top. This is known as nitrogen family. And the 16th group is known as oxygen is coming first. It is known as oxygen family. And the 17th group is known as halogens. Halogens means they are highly electronegative elements. And the last, it is noble gases. The last shell is last group is known as noble gases or zero group elements or discrete elements. They are coming in a 3 name. Okay, these are the simple outlook of a periodic table. You can see that the left side you can see it is fully covered with metals. When you coming to the period wise, you can see the right side will be full of non-metals. You can see metalloids here. Okay, the left of the periodic table it is metals. This is fully non-metals. Okay, and this is a transition metals. This is a simple outlook of a periodic table, and I have told you that in a group wise, the elements are having same valency. Group wise, the elements have the same valency, and they have similar chemical property also. Similar chemical property also. Let's see some example.
For example, lithium, sodium and potassium being in the same group have a valency of 1. On the other hand, when we move from left to right across a period, the electrons successively get added in the same outer shell. Okay, the atomic number 2 increases in exactly the same order.
Okay students, just like a Mendeleev's periodic table, across the period you can see that elements and the atomic configuration, electronic configuration is entirely different.
In the first period, only 2 elements exist, hydrogen and helium. This comes from the fact that the first shell can accommodate the maximum of only 2 electrons. In fact, in both these elements, only the first shell is occupied by the electrons. The second period begins with the lithium that contains only 1 electron in the second shell. Look at beryllium here. It has 2 electrons in the second shell. As we move towards the right, electrons keeps adding in the second shell until it gets full. It ends with the neon, okay, which has 8 electrons in the second shell. Now, if we count from lithium, we observe that there are 8 elements in the second period. Got it? Now, in the third period that begins with sodium, the electron keep increasing till argon, where 8 electrons get filled in the third shell.
Okay, so when you have a hydrogen and helium, you have observed there, right? And you know what is Bohr-Bury rule? The Bohr-Bury rule or 2n square rule. The 2n square rule states that the number of electrons in each of the shell is fixed. The K shell, the maximum accommodation is 2. How it became 2? K shell means n is equal to 1, first shell, right? So 2 into 1 square is equal to 2. According to 2n square rule, L shall have maximum accommodation 2 into, what is the n? N is equal to 2 since it is second shell, which is equal to 8. M shell with the, how many electrons? 2 into, M shell is the third shell, so 3 square. Substitute the value, you will get 18. N shell means the fourth shell, 2 into 4 square, which is equal to 32. This was the Bohr-Bury rule. Okay, this is the Bohr-Bury's first rule. But students, we know that octet rule also put forward by Bohr-Bury. What is octet rule? Yes, the outermost electrons, the outermost shell should ended up with 8 electron. That rule is known as octet rule. So in order to follow the octet rule, okay, what we have to do, what we can do is that the rest of the elements, when you consider, you can classify how many elements were there according to the Bohr-Berry rule. According to the Bohr-Berry rule, you can say that first shell with 2 electrons are maximum, right? So how many elements are present in the first row? First period, 2 elements are present, right? Hydrogen and helium. Okay, look at the second period. What are the second period? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. How many electrons? Yes, you can see how many 8 electrons in the outermost shell according to the Bohr-Berry rule. We know that. Okay, so how many elements are present in the second row? 8 elements. But coming to the third row, the third period, there also you can see the outermost electrons are ended up with 8 electron. When you take sodium, magnesium, aluminium, silicon, phosphorus, sulfur, etc., the outermost shell, the outermost electron is ended up with the third electron, right? Yes. That is why the 8 elements are there present. Last electron is ended up with the 8th shell. Or when you go to the next shell, that is potassium, starting with potassium. This you can see 4 shells are there. But according to Bohr-Berry rule, you can see 18 elements were there. Right? 18 elements were there in the 4th period. Coming to the 5th period, there are also 18 elements were there. And coming to the 6th and 7th row, you can see that the 6th row, after lanthanum, you can see there is one more row, that is lanthanide. So total it is 32 elements. And this also after actinium, you can see the next actinium is there, that actinoids are there. So total 32 elements were there. Okay, so according to the Bohr-Berry rule, that is 2n square rule, so by looking at the 2n square rule, you can predict how many elements are present in each of the period. Okay, so while writing the electronic configuration, follow the octet rule. Follow the octet rule. But by looking at by substituting the value of n, you can see how many elements are present in each of the period. That is one of the merit of the Bohr-Berry rule. Children, still I have a doubt. Where is the position of hydrogen? Is it possible to keep it here along with first metals, alkali metals? Or is it possible to place it with the 17 alkali metals? Sorry, 17 halogens. Where we should place? Since hydrogen can react with, how it can react these metals? Like same way hydrogen can react. And hydrogen can react with those metals, those non-metals also. Those halogens also can react with the hydrogen. Both show the same property. This also will show the similar property and this also will show the similar property. This can make compounds with hydrogen. Either with the halogens or with the alkali metals. Where we should place hydrogen? That is a question that we will discuss in the next class. Okay?